Hello, everybody. So this is the final lecture in computer science. This is called algorithm analysis, which is really a question of how do you know whether one algorithm is good or bad? So let's take a look. So the whole subject of algorithm analysis is really one that's very, relies a lot on mathematics. So we're not going to go into too much math here, but there will be time when there is a little bit. Um, So an algorithm has to solve a problem. An algorithm is just a way of solving a problem, and it should solve it efficiently. Efficiently here means either efficient use of time, how fast it takes to solve the problem, or efficient use of space. In other words, how big is the program? How much memory does it occupy? Is it too big, and so forth. So the big concern is not so much space, because there's a lot of memory. Memory keeps doubling every bunch of years. But it's really a question of time, because some algorithms have to solve problems super fast, right? So if you think about like navigation systems where they have to make pretty quick decisions, even in a fast computer, decisions have to be made fast. So it can't be any lull, it can't be any stutter, and the solution has to be quite fast. So efficient use of time is really the key. So that's what we're going to focus on. So how do we measure how fast an algorithm is? Well, you know, a crude way of doing it might be just to use a stopwatch and time it, but timing is way too fast. Algorithms take hundredths of a second. There's no way to really do that except to use the internal clock of the computer. What's wrong with that is it then depends on the particular computer you're running this algorithm on, which may not be the same for all computers. Supercomputer might run much faster, for instance, than a laptop. And so measuring it on a supercomputer may not be good because it may not run so fast on a laptop and so forth. So that's not what computer science people do. What people in computer science do is they have a way of measuring algorithms, and it's called running time. So a running time is measured in the following way. So it uses what's called big O notation. Big O is a capital O, and capital O is just simply a way of categorizing algorithms. So for example, the very fastest algorithms that have no loops, no looping structures at all, and are simply a sequence of statements one after the other, are called order one algorithm. And it doesn't really matter whether they're 5 statements or 500 statements. If there's no looping structure, then they're all categorized in a single order one algorithm. So obviously all the projects you guys did, except for one, which was the bumper car project, was the only problem where you had looping structures of any seriousness, the bumper car project. So now we're going to look at the most important algorithm in computer science, the search problem. Like, how does a computer search? Well, if you think about it, computers are searching a lot, right? They're searching every time you click on something, it's searching for it, files, folders, text, internet locations, music, videos, whatever. It's doing a lot of searching. Every time you click on something, it has to go find that particular program and run it. Every time you click on something on an internet site, it has to find that particular link and what it's attached to and go get it. So searching is very important. And this is what we're going to focus on today. And this is what is focused on your exam. So there are 2 ways of searching. First of all, how do you search if your list was not alphabetized? If you had a chaotic phone book or any kind of a list of things where everything was out of order, there was absolutely no order to it, the only way to search is by using what is known as the sequential search. Sequential search is where you go, what? You start from the beginning of the list and you simply compare that item to what you're looking for. And if it's the same, you're done. If it's not, you just go on to the next item in the list. So you just keep basically going from the top of the list to the bottom of the list, looking for what you want. That's not a very good algorithm, but it's the best you can do if the list is unordered, has no order to it whatsoever. So what's the running time of this algorithm? It's clearly not order 1 because it depends on what? Well, it depends on the size of the list. So the size of the list we'll call n items in the list. It's a single looping structure, if you were to code this, and it is called an order n algorithm. So this is what you need to know for the test. Sequential search, start from the beginning of the list, make your way through until you find what you're looking for or you get to the bottom of the list, and that is known as an order n algorithm. So then the question is, well, is there a better way? Well, no, there isn't if the list has no order to it. So the key is to create a list that does have order to it. And if it does have order to it, then there is a better way. And that is known as the binary search. How does the binary search work? Well, imagine you have order to this list, let's say alphabetical order. So let's say you're looking for somebody whose last name starts with an L. You might improve this because you don't have to go from the beginning to the end. You can sort of go somewhere into the middle of the list. So you start your probe, no matter what you're looking for, somewhere in the middle of the list. And if you know that if you stare down at that particular letter, let's say you're staring at the M's, you know that what you're looking for is in the first half of the list. And you can sort of toss out the second half of the list because it's not anywhere from M to Z. The person you're looking for has a last name that begins with an L. So then you continue to have the remaining part of the list. So you keep cutting the list in half and throwing out the half of the list where what you're looking for doesn't exist, and keeping the half of the list that contains what you're looking for. By doing that, you will get your answer really fast. So let's analyze this a little more carefully. So how does this work? Well, let's say we have n items in a list and we have yet to probe the list. No probe. We haven't looked into the list to say, is that what I'm looking for? Yes or no? So the first time we probe into the list, what happens? After one probe, you've eliminated half the list, and what you have left is half the list. After two probes, you only have a quarter of the list left because you eliminated half of the half that you looked at, right? So you had half the list, you could throw away half, and that leaves you with half of the list, which is a quarter. If you keep doing this, 3 probes, you only have 1/8 of the original list left. So the question might be, one little question is, what if you had 32 items in the list? How many probes, in the worst case, would it take you to find what you're looking for? I'll give you 2 seconds. 1, 2. Well, the answer is 5. Why? Because after 5 probes, there would be n over 32 items left in a list, and 32 is n in this particular case, and 32 over 32 is 1. So you'd be left with the one you're looking for. So what's the formula in this particular case? The formula here basically is that 2 to the number of probes is equal to n, where number of probes is the exponent, right? 2 to the number of probes power is equal to n. Well, a little bit of pre-calculus, and you can solve this equation for the number of probes. And that equation uses logarithms. Don't worry, this is not on your test. The only thing that I'm asking you on this test is the basic idea of binary search and the basic idea of sequential search. So in this particular case, the number of probes is called log base 2 of n. So we call this binary search is known as a order log n algorithm, right? LG means base 2, log of base 2. All right, so that's a special abbreviation for log base 2 of n. So then the question is, well, how much faster is it than sequential search? So I'm going to go off into a whiteboard here for a second. whiteboard. There we go. Sorry. Okay. So we're going to take a look at how much faster binary search is compared to sequential search. So let's start with a certain number of items in a list, n, and let's compare it to an algorithm that's order n versus the algorithm binary search that's order log n. Okay, so for example, let's take big numbers, right? So let's take a big search space such as we might have in today's world, which is, let's say, n is 10 to the 10th. Well, how long, we have to make a certain assumption that let's make the assumption that a probe, a single probe in either case, that means, is this what I'm looking for? Takes 10 to the minus 3 seconds, or 1,000th of a second. It doesn't really matter what the real number is, it's just the same for every particular case. So if a probe takes 10 to the minus 3 seconds, how long does a sequential search take? Well, the answer is 10 to the minus 3 times 10 to the 10th seconds, which is 10 to the 7th seconds. Well, that's 10 million seconds. 10 million seconds is really a long time, right? You can figure out, you have 60 seconds in a minute, you have 60 minutes in an hour, that's 3,600 seconds in an hour, and keep going, and you have days, right? So this would take days, no good. What about binary search, log n, same assumption. Well, this is the same as 10 to the minus third times the log of 10 to the 10th. Well, the log of 10 to the 10th is the same thing as 10 times the log of 10, right? That you can take the exponent and pull it on the outside. Those of you in pre-calculus may know this. Well, the log of 10 means what? It means 2 to what power is 10? Well, 2 to the third power is 8, 2 to the fourth power is 16. So let's estimate that. I think it's pretty close to 3.3. So what do we have? We have 3.3 times 10 to the minus third times 10 to the first, right? So 10 to the first times 3.3 is 33. So this is about the same thing as 3.3 times 10 to the minus second, or 0.033 seconds. So you can see that the binary search here, this is binary search, is way, 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 way faster than sequential search, order n. Like big time faster, like 10 to the 9, like a billion times faster. You have to multiply that by almost a billion times, 10 to the 9th to get, you have to multiply that by 10 to the 9th to get that. So it's about a billion times faster. So that's extraordinary. Well, let's even go further than that. Doing the same thing. Let's suppose we're in the future and n is really, really big, right? Let's say n is about approximate an upper bound for the number of molecules that are in the universe. That means how much matter is in the universe. And if you look at all the molecules in the universe, a friend of mine, physics person, said it's definitely less than 10 to the 90th. So what happens if we look at 10 to the 90th? Well, the running time of order n on 10 to the 90 is ridiculous, right? It's longer than the universe has been around for, and not possible, right? It's way longer than since the Big Bang. But if we look at the order n algorithm, again, binary search, order n algorithm, we have 10 to the minus third times 90 on the outside times the log of 10. And 90 log of 10 is still 3.3. So this is 3.3 times 90 times 10 to the minus third. Well, 90 times 3.3, 90 times 3 is 270. 90 times 3.3, let's call that 300, or roughly 300 times 10 to the minus third is 0.3 seconds, right? So not bad. So what do we conclude from this? We conclude from this that a search space that is as big as the number of molecules that are in the universe, which means impossibly large, will always be achievable through a binary search, right? But sequential search can't be done. And that's what you need to know for the test. Actually, all you need to know for the test is the difference between sequential search, going through a list, first item through the list, down to the last item sequentially, or binary search where you have the list each time much faster. That is all for the computer science concept lectures.